Module 9, Good Manufacturing Practice, Heating, Ventilation, and Air Conditioning HVAC Systems. About this module. Follow the prompts on the screen to navigate through the module. Quick quiz questions appear throughout the module. These are simple knowledge tests and are not scored or used in your final assessment. Final assessment at the end of the module is your opportunity to demonstrate your knowledge, and you will receive a score on these questions. All answers have appeared in the learning material. Navigation tip. Screens are interactive. Navigation prompts may occur at the top or bottom of the screen. Objectives. The objectives of this e-learning presentation are to understand critical design attributes of clean room HVAC, commissioning and qualification expectations, requirements for control and maintenance of system, parameters to be monitored and recorded, operational requirements around manuals, training, and procedures. Introduction. GMP regulations require a quality approach to manufacturing, enabling companies to minimize or eliminate instances of contamination, cross-contamination, mix-ups, errors, increased traceability. In pharmaceutical manufacturing, how environmental conditions impact the product being made is of primary importance. Introduction continued. HVAC play an important role in ensuring the manufacture of quality pharmaceutical products. Prevention of contamination and cross-contamination are an essential design consideration of an HVAC system. A well-designed HVAC system also provides protection to the environment, protection to the operators, comfortable working conditions. The design of the HVAC system should be considered at the initial design stage of a pharmaceutical manufacturing plant. Introduction continued. HVAC system design influences architectural building design and layout, e.g., airlock positions, doorways, and lobbies. These in turn influence room pressure, pressure differentials, pressure cascades, contamination and cross-contamination control. Introduction continued. Temperature, relative humidity, and ventilation should be appropriate and should not adversely affect the quality of pharmaceutical products during their manufacture, storage, accurate functioning of equipment and instruments. A comprehensive science and risk-based approach should be followed throughout the life cycle of an HVAC system, including its design, qualification, and maintenance. What is a clean room area? An area or room or zone with defined. Introduction continued. Temperature, relative humidity, and ventilation should be appropriate and should not adversely affect the quality of pharmaceutical products during their manufacture, storage, accurate functioning of equipment and instruments. A comprehensive science and risk-based approach should be followed throughout the life cycle of an HVAC system, including its design, qualification, and maintenance. Risk assessment is not a substitute for GMP. What is a clean room area? An area or room or zone with defined environmental control of particulate and microbial contamination, constructed and used in such a way as to reduce the introduction, generation, and retention of contaminants within the area. WHO 2018. Clean room classifications are established by measurement of the number of particles 0.5 micron and larger that are contained in 1 cubic foot of sampled air. Types of clean room classes: A, B, C, D. Critical and controlled: level 1, 2, or 3. ISO 4.8, 5, 7, 8. What HVAC can do. Areas of manufacturing should be classified as clean areas, clean zones, clean rooms, or controlled areas. HVAC can control airborne particles, dust, and microorganisms, air filtration HEPA or fine filter as appropriate. Maintain room pressure. Maintain positive or negative pressure relative to adjacent room as appropriate. Manage relative humidity. Maintain space temperature. HVAC can't clean up contaminated surfaces, rooms, or equipment. Compensate for workers who do not follow procedures. Air cleanliness classes. The table below, derived from U.S. Federal Standard 209E, shows the air cleanliness classes. Table interpretation. 1. Class 100, M 3.5, is the area where the particle count must not exceed a total of 100 particles per cubic foot, 3,530 particles per cubic meter, of a size 0.5 microns and larger. 2. Class 10,000, M 5.5, is the area where the particle count must not exceed a total of 10,000 particles per cubic foot, 353 100,000 particles per cubic meter, a size 0.5 microns and larger, or 70 particles per cubic foot, 2,470 particles per cubic meter, of a size 5.0 microns and larger. 3. Class 100,000, M 6.5, is the area where the particle count must not exceed a total of 100,000 particles per cubic foot, 3,530,000 particles per cubic meter, of a size 0.5 micron and larger, or 700 particles per cubic foot, 24,700 particles per cubic meter, of a size 5.0 microns and larger. European Community Guidelines and WHO. European Community defines clean rooms in alpha grades A, B, C, and D. The classification is given on 2 different conditions: at rest, in operation. At rest is the condition where the production equipment is installed and operating, but without any operating personnel. In operation is the condition where the installation is functioning in the defined operating mode with the specified number of personnel working. European Community Guidelines and WHO continued. Grade A classification is the most stringent of all. It requires air in the immediate proximity of exposed sterilized operations to be no more than 3,500 particulates per cubic meter, in a size range of 0.5 micron and larger, when measured not more than 1 foot away from the work site and upstream of the airflow during filling-closing operations. This applies both at rest and in operation condition. Grade A areas are expected to be completely free from particles of size greater than or equal to 5 micron both at rest and in operation condition. Besides at rest and in operation clean room states, another condition most commonly used by HVAC contractors is as-built condition. As-built clean rooms are those which are ready with all services connected but without equipment and personnel. Level of air cleanliness. The level of air cleanliness for different areas should be determined according to, but not limited to, the products manufactured, the process used, the product's susceptibility to degradation. Where a clean room classification is specified, the manufacturer should state whether the classification is rated for as built, at rest, operational condition. As built bare room without equipment or personnel. Grade A classification is the most stringent of all. It requires air in the immediate proximity of exposed sterilized operations to be no more than 3,500 particulates per cubic meter in a size range of 0.5 micron and larger when measured not more than 1 foot away from the work site and upstream of the airflow during filling-closing operations. This applies both at rest and in operation condition. Grade A areas are expected to be completely free from particles of size greater than or equal to 5 micron, both at rest and in operation condition. Besides at rest and in operation clean room states, another condition most commonly used by HVAC contractors is as-built condition. As-built clean rooms are those which are ready with all services connected but without equipment and personnel. At rest, equipment may be operating, but no operators present. Operational, normal production process with equipment and personnel. Controlled conditions. The manufacture of pharmaceutical products should take place in a controlled environment. The design of the HVAC system should be closely coordinated with the architectural design of the building. Infiltration of unfiltered air into a manufacturing facility should be prevented. Can be a source of contamination. Manufacturing facilities should normally be maintained at a positive pressure relative to the outside to prevent the ingress of contaminants. Where facilities are to be maintained at negative pressures relative to the outside, special precautions should be taken to mitigate any risks, e.g., beta-lactams, potent cytotoxic, etc. Controlled conditions. Continued. HVAC systems should ensure that room conditions are attained through heating, cooling, air filtration, air distribution, airflow rates, air exchange rates. Containment, cleanliness, and protection. Containment, cleanliness, and protection may be facilitated through, for example, correct building layout, building finishes, the use of airlocks such as personnel airlocks, PAL, and/or material airlocks, MAL, pass-through hatches, PTH, change rooms and passages, sufficient pressure differentials. Design of HVAC systems. Air, whether it is from outside or recirculated, acts as a vehicle for bacterial and gaseous contaminants brought in by the movement of people, material, etc. Some of these airborne contaminants are harmful to products and people. Their removal is necessary on medical, legal, social, or financial grounds. There are two main sources of particulates: external, internal sources. Design of HVAC systems continued. External sources consist of the following: outside makeup air introduced into the room. This is typically the largest source of external particulates. Infiltration through doors, windows, and other penetration through the cleanroom barriers. Controlling action: make-up air filtration, room pressurization, sealing of all penetrations into the space. Design of HVAC systems continued. Internal sources consist of the following: people in the clean area. People are potentially the largest source of internally generated particulates. Clean room surface shedding, process equipment, material ingress, manufacturing processes, controlling action, design airflow path to shield humans from surroundings, use of air showers to continually wash occupants with clean air, using hard-surfaced, non-porous materials such as polyvinyl panels, epoxy painted walls, and glass board ceilings. Proper gowning procedures, headwear. Design of HVAC systems continued. HVAC in pharmaceutical industry affects a number of issues, starting with the selection of building materials and finishes, the flow of equipment, personnel, and products, determination of key parameters such as temperature, humidity, pressures, filtration, airflow parameters. It also governs the level of control of various parameters for quality assurance, regulating the acceptance of criteria, validation of the facility, and documentation for operation and maintenance. Design of HVAC systems continued. HVAC systems should be appropriately designed and managed throughout their life cycle. Documentation such as schematic drawings should be maintained to reflect the current situation. Risk management principles should be applied for HVAC systems. This includes, but is not limited to, appropriate design, operation and monitoring, control of the climatic conditions, the prevention of contamination, cross-contamination. Design of HVAC systems continued. The HVAC system capacity should consider room leakage, duct leakage, filter conditions. Materials of construction of HVAC system should not be a source of contamination. Ducting, piping, fittings, sensors, and other components should be clearly marked or labeled for identification and direction of flow. Air intake and exhaust air terminals should be positioned in such a way that prevent cross-contamination. Air handling units, AHUs, should be provided with properly designed drains to remove any condensate that may form in them. Design of HVAC systems continued. Recovery rates should be specified and achieved to demonstrate that the HVAC system is capable of returning an area to a specified level of cleanliness or classification, temperature, relative humidity, room pressure, and microbial limits within the specified time. Failure mode and effect of critical components should be analyzed. The analysis should include possible room pressure changes due to fan failure and the possible impact of partial system shutdown on ease of opening doors for escape purposes. Air supply and extract grills should be appropriately located so as to effectively flush rooms and to prevent zones of stagnant air. Design of HVAC systems continued. Automated monitoring systems should be capable of indicating any out-of-limit condition by means of an alarm or similar system. If such systems are identified as GXP systems, they should be appropriately validated. Alarm systems should be in place to alert personnel in case of failure of a critical component of the system, e.g. a fan. The effect of fan failure on building and HVAC components should be assessed. If applicable, provision should be made for a fan interlock failure matrix. Design of HVAC systems summary. The efficacy of the HVAC system design is based on proper consideration of the following factors: air handling system, duct system design and construction, selection, location, and mounting of filtration system, defumigation requirements, commissioning, performance qualification and validation, testing and validation, documentation. Design of HVAC systems summary continued. The efficacy of the HVAC system design is based on proper consideration of the following factors: building construction and layout design, defining the HVAC requirements system-wise and then room-wise, cleanliness level, room temperature, relative humidity, room pressure, airflow pattern, cooling load and airflow compilation, selection of airflow pattern, pressurization of rooms. Full fresh air systems and recirculation systems. Full fresh air or recirculation type HVAC systems may be used. Fresh air should be adequately filtered to remove contaminants. Recirculation systems should pose no risk of contamination or cross-contamination. HEPA filters may be installed in the supply airstream or return airstream to remove contaminants and prevent cross-contamination. The HEPA filters should have an EN 1822 classification of at least H13 or equivalent. Full fresh air systems and recirculation systems continued. HEPA filters may not be required to control cross-contamination if cross-contamination can be avoided by other robust technical means, the air handling system is serving a single product facility, the amount of fresh air intake required should be determined based on sufficient volume of fresh air to compensate for leakage from the facility and loss through exhaust air systems. Operator occupancy, regional or national legislation. Full fresh air systems and recirculation systems continued. Recirculation of air contaminated by organic solvent or highly hazardous materials must be avoided. The need for and the degree of filtration of the exhaust air should be based on risk, exhaust air contaminants, local environmental regulations. Full fresh air systems and recirculation systems continued. Completely fresh air. Air is conditioned, enters production area, and is vented and discarded. Advantages of this system: fresh air, lots of it. Can handle hazardous materials, although will need to clean up air leaving the space. Exhaust duct is usually easy to route as high velocity equal smaller diameter. Disadvantages: expensive to operate, especially when cooling and heating. Filter loading very high equal frequent replacement. Potential need for dust collection / scrubbers / cleanouts. Full fresh air systems and recirculation systems continued. Completely fresh air. Applications: labs with hoods. Potential hazards: bulk pharmaceutical chemical, API, plants handling flammable materials, Oral solid dosage, OSD, plants where potent products, materials exposed, where high potential of product cross-contamination or segregation. Some bio-API facilities with exposed potent materials. Full fresh air systems and recirculation systems continued. Completely fresh air. The diagram shows a completely fresh air system. Full fresh air systems and recirculation systems continued. Recirculated air. Advantages. Usually less air filter loading equal lower filter maintenance and energy cost. Opportunity for better air filtration. Less challenge to HVAC equal better control of parameters, T, RH, etc. Less throwaway air equals lower cooling heating cost. Disadvantage. Return air ductwork routing to air handler may complicate above ceiling. Chance of cross-contamination equals requires adequate supply air filtration and sometimes return air filtration. Full fresh air systems and recirculation systems continued. Recirculated air. The diagram shows a recirculated air system. Air filtration, airflow direction, and pressure differentials. Measures should be taken to prevent cross-contamination in multi-product facility, as different products can be manufactured at the same time in different areas or rooms. The following can assist in cross-contamination prevention: facility design and layout, appropriate levels of filtration, airflow direction, pressure differentials. Air filtration, airflow direction, and pressure differentials continued. Air filtration. Proper air filtration is crucial for clean room controls. Degree of filtration of air is important to prevent contamination. Type of filters to be used is dependent on quality of ambient air, return air recirculation, air change rates, national requirements, products and required class of cleanroom, etc. Air filtration, airflow direction, and pressure differentials continued. Air filters. Air filters capture solid materials. Can be roughing filter to capture a significant percentage of total mass, 30%. Can be high efficiency to capture a higher percentage of mass plus some of the weightless fine particles, 85% to 95%. Can be high efficiency particulate to remove virtually 100% of the material weight and 99.97% or more of all particles. Air filtration, airflow direction, and pressure differentials continued. Air filter level of protection and type, based on ISPE oral solid dosage OSD guidelines. Level 1. General conditions. Area with normal housekeeping and maintenance where there is no potential for product contamination, e.g. warehousing. Level 2. Protected conditions. Area in which steps are taken to protect the pharmaceutical starting material or product from direct or indirect contamination or degradation, e.g. secondary packing, warehousing, first stage change rooms. Level 3. Controlled conditions. Area in which specific environmental conditions are defined, controlled, and monitored to prevent contamination or degradation of the pharmaceutical starting material or product, e.g., where product, starting materials, and components are exposed to the room environment, plus equipment wash and storage areas for equipment product contact parts. Air filtration, airflow, direction, and pressure differentials continued. Levels of protection and recommended filtration. Level 1 protection. Primary filters, e.g. EN779G4. Level 2 protection. Production are with 100% outside air, primary plus secondary filter, e.g. EN779G4 plus F8 or F9 filters. Level 3 protection. Production facility operating on recirculated plus ambient air where potential for cross-contamination exists. Primary plus secondary plus tertiary filters, e.g. EN779G4 plus F8 plus EN1822H13 filters. For full fresh air system without recirculation, G4 and F8 or F9 filters are acceptable. Air filtration, airflow direction, and pressure differentials continued. HEPA filters, high efficiency particulate air filters, have 99.97% to 99.997% removal efficiency of 0.3 micron particles. Less than 0.03% of all particles of 0.3 microns or larger can get through such a filter. The level of pre-filtration needs to be considered to reduce the particle load on the filter. Sub-micron glass fiber media housed in an aluminum framework and are available in two types of constructions. 1. Box type. 2. Flanged type. Air filtration, airflow direction, and pressure differentials continued. Box type HEPA filters. Air filtration, airflow direction, and pressure differentials continued. Flange type HEPA filters. Air filtration, airflow direction, and pressure differentials continued. Airflow direction pattern. Filtered air entering a production room or covering a process can be turbulent, unidirectional, laminar. Two facets must be considered. GMP aspect. Unidirectional air, laminar installations give a better protection because of the displacement effect rather than the dilution effect. Economical aspect. Turbulent air installations are cheaper as less air has to be treated. Air filtration, airflow direction, and pressure differentials continued. Turbulent, non-unidirectional airflow pattern. In the case of a vertical unit, a low return air exhaust is more favorable as the air is better distributed in the room. Air filtration, airflow direction, and pressure differentials continued. Unidirectional airflow pattern. For certain operations, e.g. in Class A laminar flow must be used. The use of barrier technology systems, isolator technology, is highly recommended in cases of operations in Class A or for sterility testing operations. Turbulent flow within an isolator is considered as equivalent to or better than grade A laminar flow in an open hood, e.g. for aseptic processing operations. Sampling and weighing area classification, same as other processing areas following sampling and dispensing. Dust contaminant should be shown through smoke test as part of validation qualification. The location and type of return and exhaust grills are important. Cleaning and maintenance are important. Air filtration, airflow direction and pressure differentials continued. Unidirectional airflow pattern. The vertical downflow configuration is preferred. Laminar workstations with vertical flow require 0.3 meters per second velocity, whereas horizontal workstations require 0.45 meters per second velocity. Air filtration, airflow direction, and pressure differentials continued. Pressure differential concept. Used where there is low dust in areas alone or in combination with other control techniques. High pressure differential, low airflow, and airlocks. Airlock types include cascade, sink, and bubble type. See next slides. Sufficient pressure differential required to ensure containment and prevent flow reversal, but not so high as to create turbulence. Consider effect of other items such as equipment and extraction systems in cubicles. Air filtration, airflow direction, and pressure differentials continued. Pressure differential concept. Air filtration, airflow direction, and pressure differentials continued. Room pressure differential indication should be provided. This may be by pressure gauges or suitable electronic systems, EMS or BMS. Where pressure indication gauges are provided, they should have a range and graduation scale that enables them to be read to an appropriate accuracy. The normal operating range, alert and action limits should be defined and displayed at the point of indication or EMS, BMS. Room pressure should be traced back to representative ambient pressure. Air filtration, airflow direction, and pressure differentials continued. The pressure control and monitoring devices used should be calibrated. Compliance with specifications should be regularly verified and the results recorded. Pressure control devices should be linked to an alarm system which is set according to the levels determined by a risk analysis and justified dead times. Zero setting of gauges should be tamper-proof. Zero setting should be checked at regular intervals. Where airlocks are used, the pressure differentials selected should be appropriate. When selecting room pressure differentials, transient variations such as machine extract systems and their impact should be taken into consideration. Air filtration, airflow direction, and pressure differentials continued. Airlocks and material pass-through hatches, PTH, can also be used for separating two different zones. PTHs fall into two categories: dynamic PTH, passive PTH. Dynamic PTHs have an air supply to or extraction from them and can then be used as bubble, sink, or cascade PTHs. Air filtration, airflow direction, and pressure differentials continued. Cascade airlock. Higher pressure on one side of the airlock and lower pressure on the other. Air filtration, airflow direction, and pressure differentials continued. Bubble airlock. Higher pressure inside the airlock and lower pressure on both outer sides. Air filtration, airflow direction, and pressure differentials continued. Sink airlock. Lower pressure inside the airlock and higher pressure on both outer sides. Temperature and relative humidity. Temperature and relative humidity, RH, should be controlled, monitored, and recorded. Limits for minimum and maximum room temperatures and RH should consider materials and products. Low RH areas need well-sealed walls and ceilings and preferably airlocks. Temperature and relative humidity continued. Controls should be in place to ensure that the HVAC system to remain effective where steam or humidity is present. Precautions should be taken to prevent moisture migration that may increase an uncontrolled load on the HVAC system. Where humidification or dehumidification is required, it should not be a source of contamination. Dehumidification and cooling systems should be well drained. Quick Quiz 1. Select the best answer and click Submit. Which of the following parameters would not form a component of ongoing monitoring of a HVAC system? A. Pressure differential pressure reading. B. Airflow pattern. C. Raw material availability. D. Cleanliness particulate measurement. Dust, vapor, and fume control. Dust, vapors, and fumes could be sources of contamination and should be appropriately controlled. If possible, they should be removed at source. The HVAC system should not normally serve as the primary mechanism of dust control. Dust extraction systems should be appropriately designed and installed. Should not be able to flow back in the opposite direction, e.g., in the event of component failure or airflow failure. The transfer velocity should be sufficient to ensure that dust is carried away and does not settle in the ducting. Dust, vapor, and fume control continued. The dust extraction points should be positioned to prevent dust and powders from dropping down from the extract point. Air should not flow through the dust extraction ducting or return air ducting from the room with the higher pressure to the room with the lower pressure. Periodic checks should be performed to ensure that there is no buildup of dust in the ducting. Dust extraction systems should be interlocked, where appropriate, to relevant AHU to avoid any risk or any impact on pressure cascade imbalances. Dust, vapor, and fume control continued. Where possible, dust and vapor removed at source. Ensure adequate transfer velocity in extraction system to prevent dust settling in ducting. Risk analysis, airflow direction. Normally air supplied through ceiling diffusers and air extracted from low-level rear. Extraction of vapors. Consider density of vapor. Handling harmful products. Additional steps needed, e.g., barrier technology, glove boxes. Totally enclosed garments with air-breathing systems. Fresh air rate supply. Comfort, odor, and fume removal, leakage, pressure control, etc. Dust, vapor, and fume control continued. The schematic shows air being supplied from the top and sweeping through the room, removing particles and exhaust air moving out at the lower level. Dust, vapor, and fume control continued. Mobile type dust collectors can become the source of contamination if not used, cleaned, and controlled in the correct manner. Quick Quiz 2. Select the best answer and click Submit. Which element of a clean room environment is not impacted by the HVAC system? A. Temperature. B. Humidity. C. Particulate count. D. Gowning. Protection of the environment. Waste from dust extraction and collection systems should be disposed of in an appropriate manner. Dust slurry should be removed by suitable means, for example, a drainage system or waste removal contractor. Qualification. HVAC systems should be qualified to ensure continued performance in accordance with specifications and achievement of the conditions as specified. Risk management principles should be applied to determine the scope and extent of qualification. The qualification of the HVAC system should be described in a master plan. The master plan should define the nature and extent of testing, the test procedures, and protocols to be followed. The procedures followed for conducting the tests should be in accordance with the appropriate parts of the standard as mentioned in ISO 14644-8 and relevant WHO guidelines, WHO and EU PICS Annex 1 are relevant for ongoing monitoring. The design condition, operating ranges, alert, and action limits should be defined. Alert limits should be based on system compatibility. Qualification continued. There should be SOP describing the action to be taken when alert and action limits are reached. This may include temperature, relative humidity, supply air quantities, return air or exhaust air quantities, room air change rates, airflow pattern tests, unidirectional airflow velocities, room pressures, pressure differentials, containment system velocities, HEPA filter penetration tests, room particle count tests, duct leakage tests, materials of construction, microbiological counts, dedusting and dust extraction systems. Qualification continued. Routine or periodic revalidation. The frequency should be established based on, for example, risk, the type of facility, the level of product protection necessary, performance of the system, the extent of routine ongoing monitoring activities. Any change to the HVAC system should be handled according to a change control procedure. The extent of qualification or requalification should be decided based on the scope and impact of the change. Maintenance. Operation and maintenance, O&M manuals. Procedures and records should be available and kept up to date with details of any system revisions made. O&M manuals, schematic drawings, protocols, and reports should be maintained as reference documents for any future changes and upgrades to the system. Maintenance continued. O&M manuals typically contain the following information: system description, operating instructions, troubleshooting, commissioning data, maintenance instructions, list of equipment suppliers, spare parts list, equipment data capacity schedules, suppliers literature, control system description, electrical drawings, as-built drawings. Maintenance continued. There should be a planned preventive maintenance program for the HVAC system. The details of this program should be commensurate with the criticality of the system and components. Maintenance activities should not have any negative impact on product quality and should normally be scheduled to take place at appropriate times, for example, outside production hours. In case of system stoppages, appropriate quality management system procedures should be followed. Where necessary, the root cause and impact should be assessed and appropriate corrective and preventive action taken. Where necessary, qualification or re-qualification should be considered. HEPA filters should be changed by a competent person, and this should be followed by installed filter leakage testing. Records should be kept for a sufficient period of time. Case study: the importance of appropriate environmental controls. The problem. This case study involves a problem that should never have been allowed to happen and cost the company a lot of lost time and money. It involves a biologics manufacturer manufacturing an API using an E. coli fermentation process. It is highly unlikely that the circumstances of these events would occur today, given the improvements in technology and the improvements in regulatory expectations and industry norms. However, it provides a very good example of what can go wrong with HVAC monitoring. The company experienced 3 consecutive batch failures due to contamination with Bacillus species. Even if it were not possible to avoid the first failure, 2 subsequent failures for the same reason should never have been allowed to happen. But the company did not have procedures in place to perform failure investigations. This was not uncommon in the early days of large-scale biologics manufacturing, but common sense should prompt some kind of investigation, and the circumstances of the event should have been enough to alert the company to potential problems. However, the company was under timeline pressure and did not appreciate the value of appropriate root cause investigation. The best way to meet timelines is to do things right first time, or at least second time. The fermenter was situated in a grade D room, which meets current industry norms and expectations, but cannot be considered as best practice. The inoculation is performed in a grade A biosafety cabinet, BSC, situated in the fermenter room. This is not the norm, but may have been more common at the time of the incident. The inoculation involved an aseptic connection, and at the time tube, welders, and single-use connectors were not commercially available. There had been very few alert level excursions reported, and the company had no appreciation that there might be a problem, which may also explain why it took 3 failures before the company took any meaningful action. Background information. This slide provides further background information to help understand how the problem happened. The gowning worn for performing the inoculation step was grade D gowning, worn over street clothing. Sterile gloves were worn when performing the aseptic connection, but part of the arms of the operator were under the BSC during inoculation, and this introduced the risk of introducing microbial contamination into the BSC from the non-sterile sleeves of the grade D gown. There is also a small degree of turbulence in the best designed BSCs. Environmental monitoring, EM, was performed in the grade D room on a monthly basis. This was not unusual and is still not unusual. However, there was also no dynamic monitoring of the room during inoculation, only in the BSC. The assumption being that if any microbial contamination is introduced into the BSC, it would be detected. In addition, the alert levels were set at 50% of the action levels, the EU PICS Annex 1 recommended limits. There was no routine trending of data, and the alert limits were not based on historical data as required, even at that time, by the EU PICS Annex 1. This was the first clear non-compliance with the regulatory requirements in operation at the time of the event. Additional shortcomings of the EM program included no species identification except for action level excursions and gram stain identifications only for alert level excursions. The other major non-compliance was that the company failed to perform any kind of failure investigation following the first batch failure. This was a requirement at the time, but was not universally implemented at that time. An in-depth investigation at this point would have at least avoided the next two failures. Investigation. After the third batch failure, all activities in the suite were put on hold and a full investigation was initiated, and an investigation team was assembled, which included manufacturing, QC, QA, facilities, and a GMP consultant who immediately requested a review of the environmental monitoring EM data. The review showed that, while there had been very few alert level excursions, there had been a very clear adverse trend. The normal baseline of 0 to 10 CFU per sample for both settle plates and active viable air samples had been exceeded on numerous occasions. There were frequent counts above 10 CFU, but below the alert limits of 49 CFU per plate for settle plates and 99 CFU per cubic meter for active viable air samples. Although these limits are within the regulatory expectations for grade D, nevertheless, they are high counts for any clean room and were a clear indication of an adverse trend. Clearly, something had changed, resulting in a significant increase in the EM levels. Most recent EM samples were still available, and there was a high incidence of various Bacillus species identified, confirming that there were high levels of Bacillus getting into the fermenter room. However, there were no Bacillus species recovered from the purification suite, which was grade C, was supplied via an independent air handling unit, AHU, and had a separate entry via a personnel airlock. These findings indicate that the probable root cause was the Bacillus species that were getting into the fermenter room, and the focus of the investigation therefore turned to how these organisms could be getting into the room. Investigation continued. There was a construction site adjacent to the manufacturing site that had been generating a lot of dust from excavation for some time. This had not been considered as a risk because it was considered that the HVAC system supplying the clean rooms would filter out any contamination from the exterior of the building. However, the investigation was extended to the HVAC supply, and a number of contradictory findings were reported back to the team. The HVAC air intake for all of the AHUs was facing the construction site, and dust from the construction site was being taken into the AHUs. This had led to a need to change the pre-filters more frequently to avoid blockage. This was already known to the facilities group, but had not been reported as an issue or an adverse trend because it was not considered to be a cause for concern. The HEPA filters were tested to determine whether there were any leaks. No leaks were detected. However, swab samples taken from various locations downstream of the HEPAs showed the recovery of Bacillus spores both on the HVAC grills and in the ductwork downstream of the HEPAs in the grade D fermenter room, but not in the grade C purification suite. Investigation continued. Bacillus spores were getting through the grade D HEPA filters and were then being introduced into the fermenter during inoculation. This was determined to be the root cause of the batch failures. However, the spores were not getting through the grade C HEPAs. How could this happen? There is sometimes a lack of understanding within the pharmaceutical community as to how HEPA filtration works. HEPA filters are graded by the percentage of particles of a defined particle size that can penetrate the filter. Therefore, if the filter is challenged with a sufficiently large load of a specific particle size or smaller, some of the particles will eventually get through. The grade of HEPA required for grade D is lower than that required for grade C, and bacillus spores are very small, 0.3 to 0.6 microns in diameter. There is therefore moderate risk of penetration of spores, and the risk is higher for grade D and for grade C. This was an important lesson learnt for the investigation team. There were also a number of contributory factors that added to the risk. 1. The frequency of EM was very low. 2. There was no identification performed unless an action level excursion occurred. No such excursion occurred. 3. The alert level and the action level limits were inappropriate. The normal values, baseline values, for the viable air and settle plate samples were between 0 and 10 CFU per sample. These values were being routinely exceeded over the period prior to the first batch failure until the facility was put on hold. There was a clear adverse trend that was not being identified until the investigation commenced. 4. There was no investigation performed for the first 2 batch failures. 5. Because the inoculation was not performed using sterile gowning and all of the controls associated with sterile gowning, there was an added risk that any contamination in the room could get into the inoculum. CAPA plan. The facility remained shut down in order to carry out a number of corrective and preventive actions. These included a full clean down and number of changes to the way that the facility was operated and monitored. 1. The air intakes were repositioned in an attempt to reduce the amount of dust drawn into the AHUs. 2. An additional bank of pre-filters was introduced prior to the AHUs to further reduce the amount of dust entering the AHUs and to prolong the life of the filters in the AHUs. 3. The HVAC ducts and AHUs were decontaminated. 4. All the HEPA filters were changed and the HEPAs supplying the grade D rooms were upgraded. 5. The clean rooms were deep cleaned using a sporicidal cleaning agent. 6. Once all of these changes and the cleaning had been completed, the entire clean room suite was requalified. Consideration was also given to increasing the frequency with which the pre-filters are changed to provide greater protection to the HEPAs. This was introduced as a temporary measure until the construction project was finished. Consideration could also have been given to the introduction of monitoring the differential pressures across the pre-filters and the HEPAs in order to give an early warning of blockage, but it was not considered a high priority at the time of the investigation. CAPA plan continued. In addition to the improvements to the HVAC system, a number of other control measures were introduced as part of the CAPA plan. 1. The EM program was reviewed and revised to introduce bi-weekly monitoring in the grade D room, including dynamic monitoring during inoculation. 2. The alert limits were reviewed and revised based on trend data. 3. Quarterly reporting of EM trend data was introduced, and these data were reviewed by the Site Quality Council. 4. The alert limits were also reviewed on an annual basis. 5. Sterile sleeves were introduced during inoculation. In addition, a number of other methods were investigated for performing inoculation, including steam-through connections, tube welders, and single-use connections. Consideration was also given to upgrading the fermenter room to grade C, since the EM data available indicated that the room might be able to achieve this grade, particularly if the HEPAs were upgraded. Lessons learned. Lesson learned. A number of lessons have been learned from this event and the subsequent investigation, which are valuable to anyone designing, maintaining, or operating a clean room. 1. HEPA filters do not provide absolute filtration, and if the particle challenge is high enough and the particle size is small enough, some particles will penetrate. 2. The design of the system, the location of the air intake, the pre-filtration, and the grade of HEPA required should not only consider the grade of clean room that is required, but also the activities being performed in the clean room. The available guidances are intended as minimum requirements, and a risk-based approach based on worst-case circumstances is often needed. 3. Alert limits should be based on historical data. This is a regulatory requirement, EU PICS Annex 1, and if the alert limits in this case had been based on the normal trend, then the problem would have been picked up much earlier, even before the first batch failure. 4. The failure to investigate after the first batch failure was inexcusable. All batch failures must be investigated. In this case, an investigation of the first failure would almost certainly have prevented further failures. 5. Identification of contaminating organisms should be performed to species level if possible, and as a minimum to genus level. It is quite common to simply perform a gram stain and look at colony morphology, but this is almost a pointless exercise as it rarely gives any indication of the source of the contamination. Identification of contaminating organisms should be performed not just when an action level excursion occurs, but also when an adverse trend occurs, and certainly when there is a contamination incident. It is best practice to retain EM plates and store them at 2 to 8 degrees Celsius until any associated in-process or final product microbial testing has been completed, as this can help any subsequent investigation. References and further reading. World Health Organization, WHO, Technical Report Series, number 961, 2011. WHO Technical Report Series, Annex 8, Guidelines on Heating, Ventilation, and Air Conditioning Systems for Non-Sterile Pharmaceutical Products, number 1010, 2018. PICS GMP Guidelines. Final Assessment. Review the module before commencing your final assessment. All questions relate directly to information and principles covered in the slides. You can only attempt each question once. Question types may include true-false, drag and drop, and multiple choice. Good luck.